two resource persons from Agilent Technology India Private Limited. And first speaker is Sri Amod Yadav, M Pharma Application Engineer, LCMS, Agilent Technology. He worked as a research associate in campus, hired from UPTU, LCMS method development and validation of BA and BE, and research scientist for validation, sample analysis of stability batch in formulation of analytical department for mankind serving life. And now, since January 2018, he is working as an application engineer with Agilent. Now, I invite Sri Amod for his lecture, please.
Okay, great. Good morning. I think I'm audible to everyone. Not audible? Yeah, great. Thank you so much. So we went through a very extensive metabolomic presentation with ISBT Palanpur. So I believe everybody is refreshed. So now we will go with some technological part of QTOF. And apart from this instrumentation and their principle, like Saurabh sir will take care of the metabolomics and their importance and how we can process the data with the available software with QTOF. Okay, so what I'll cover in this session, liquid chromatography, and along with the liquid chromatography, mass spectrometry, what are the different mode of mass spectrometry, and what exactly the instrument we are having in this FRI campus, and what exactly the principle behind the QTOF and how this QTOF is differentiated from the other available mass spectrometry. So, as you know that, like this instrument is tandem with the QTOF. So LC here we are using just for the separation technique. Along with the LC, we can also use the LC detector. Like we know that with LC we can use UV, IR, FLD, ELSD. But mostly we are using UV once we are using the configuration with the LC with MS. So in which scenario we can use LC detector in case suppose we are using any impurity characterization, where we wanted to separate the molecule apart from the API main peaks with the known impurities, then we have to be separate that molecule on the UV first, then we can identify the same molecule on MS. Based on that, we can use the configuration HPLC, UV, then MS. So just coming on the mass spectrometry, first of all we have to know what exactly the principle of mass spectrometry. We know, like I know that we have went through the mass spectrometry session, so we know mass spectrometry, the principle of mass spectrometry is that the identification of molecule on the basis of their M by Z, like mass by charge ratio, we are able to identify the molecule. So we know like UV, earlier we had a detector. So what exactly like we are not able to do, then only we came on the mass spectrometry. Once we are having the many compound like mixture in our sample and they have a similar polarity index, then they are going to be separate of the same RT. In that case, we are not able to resolve the molecule or know the molecule, but if they are separate, illusion is the same RT. To know that kind of molecule having the similar polarity, we need a mass spectrometry as a detector. Because here mass is going to be identify the molecule on the basis of their mass by charge. In general, to set a chromatography, we have to be resolve the molecule on the basis of chromatography to change the polarity, and that is based on the mobile phase, that is based on the stationary by changing the column itself. But in case like if we are having the many component, then itself we have a capacity to identify the molecule on the basis of the mass spectrometry. So on further development, we had a single quarter pole, onwards we had a triple quarter pole. So what is the difference between the single quarter pole and triple quarter pole? Like we can identify the molecule on the triple quarter pole on the basis of their product ions. So why we are saying this is a triple quarter pole? Because we are having the first quarter pole then collision cell where we are doing the product, like getting the product masses by applying the collision energy, and onwards that we can identify on the basis, like confirm the molecule on the basis of the product masses. But these two technology of the mass spectrometry, single quarter pole and triple quarter pole, are unit mass resolution based. Means what? Like if we are not having them that much accurate masses on the decimal point of third and fourth digit. So what would happen? Like the monoisotopic confirmation would not be that much accurate, but actually required to confirm the molecule. So that's the reason to get the molecule on the more accurate way, we need a HRMS as a technology to do the discovery kind of analysis and non-targeted metabolite identification on the basis of their monoisotopic pattern. So to know these all the things, what is the significance of the top would be, like we'll get the more selectivity. So if we'll get the more selectivity, like we'll get the more accurate product, more accurate mass of the compound. If we'll get the more accurate mass of the compound, we can draw their accurate product masses so that we can draw the spectra of the concerned compound, and which like yield, like increase the yield of the compound somehow, like we'll target the compound and we'll focus that what exact the result we are having that is more accurate, and so somehow what we'll have the more sensitivity towards the focused compound. So wherever the industry, like where we are using the targeted analysis like proteomics, metabolomics, in that field we can use the QTOF as a technology. So we are saying that this instrument is used as a high resolution mass spectrometry. So what exactly the resolution is that? So if we are considering any profile P, so full width, half height, we are considering as and divide like molecular mass, ion mass of the compound divided by the full width of the compound would be the resolution of any profile P. So if we are acquiring any data on top, so you see that here the single quad and triple quad data acquired on the Agilent instrument. So mass difference between these two peaks is 1 Dalton only. Consider the same data once we acquire on the top and QTOF, the same instrument like resolution was 903 was on the single quad and triple quad, but the same data once we acquire on the top and QTOF, the resolution was almost 15,000. So this much resolution, like this is one of the data considering the molecule, but we can even get the better result and better resolution considering this increasing the sensitivity of the compound. So by this way we can enhance the resolution, we can get a more selectivity and sensitivity of the compound, and we will get a better result of the compound. So as having said that, we have to know about the masses, like what exactly the nominal mass, what exactly the monoisotopic mass and average mass. I believe everybody know about what exactly the difference between these. So average nominal mass is like indigenous mass of the any compound, but this instrument having the capacity to identify the molecule on the monoisotopic difference. So monoisotope is, what is monoisotope? Like the isotope which having the more abundance in nature. And average mass like average of the all element configuration. So this QTOF having the capacity to identify the molecule on their monoisotopic distribution. So somehow if we have a big, like larger the molecule and their different pattern of the monoisotope, we could be able to identify the different isotopic fidelity of the compound. So like we know that I'm saying that this is going to be give you the more accurate masses. So how we can calculate that whatever the mass and m/g value we are getting it, that is more accurate. So the specification of the instrument is that this will give you the result of less than 2 ppm. So how we can calculate the ppm error? Like measure whatever I'm getting the result divide minus theoretical value of the mass value of the compound divided by the theoretical mass into 10 to the power 6. So with the help of that, so whatever result would come, that is the ppm error of the compound, and we are claiming that the specificity of the instrument would pass only once we are getting the result less than 2 ppm. And that's the reason we are calibrating the instrument on the daily basis, so that if there would be any drift into the top would happen, that would be mitigated after the calibration of the instrument. So whatever result you would have, that would be more accurate, and it is actually as per the specification of the instrument would be less than 2 ppm.
So any doubt on this point? ppm, how we calculate ppm?
Yeah, so you can raise your question in between also, so that we can be
asked, because otherwise we go to lab also, I will show you the data. But ppm, lot of people confuse with
what exactly the component of this LCMS QTOF configuration? This is the general configuration of the LCMS. So here we are using the solvent system like this, where we are using the solvent as a mobile phase here, which would be the pump by the HPLC pump. So we are going to be configuration with HPLC and MS. So these are the HPLC module like solvent cabinet, HPLC pump, auto sampler and column compartment. Onwards that we are using MS as a detector. So we can use UV also as a detector in case if you wanted to confirm the compound on the basis of UV, then further detect the same with the mass as a detector. So after the column, it will go to the source. I'll describe also into the another pictorial diagram. So in source the desolvation would happen. So what will happen in desolvation? All the solvent along with the molecule will go into the source through the nebulizer, and at the nebulizer all the volatile solvent. That's the reason we are always recommending in mass spectrometry we have to use the solvent which is volatile in nature and should not leave any residue. Whether there might be some solvent which is volatile in nature, but they are leaving any residue, that would not be recommended for the mass spectrometry. So after this desolvation, the ion travel into the mass instrument, and in mass there is a capillary part. That capillary, through the capillary it will go to the ion guide, and from the ion guide it will go to the quarter pole. So we know that the mass filtration could happen on the basis of quarter pole principle. So I will describe in the next, like what are the different like mass spectrometry as a detector, like mass analyzer. So we have a single quarter pole, like in single quarter pole we have a one quarter pole system. So we can do the scanning there and single ion monitoring. In triple quarter, having said that, like there is a two quarter pole and one collision cell. So in first quarter pole we can pass the ion either in a scan mode, either in the selective mode, and after that whatever the mass selection you have given that in the form of the transitions, that ion only would pass this first quarter pole and reach to the collision cell. In collision cell we are applying the potential difference with the nitrogen gases, so that what this collision energy does, actually we are applying the potential difference into the collision cell. So with that potential difference, nitrogen gas movement would be fast and slow depending on that how much collision energy you are applying. So once any ion which has passed through the first quarter pole will go to the collide with that nitrogen gas and break down into the product masses. And further the quarter pole will filter only the selected product masses. That's the reason the sensitivity in quarter pole is far better. That's the reason we are always recommending quarter pole for the quantitation analysis. So, and then after the time of flight, so sensitivity will be reduced in time of flight, but mass accuracy will be high because we are using TOF as a detector. So we identify the compound on the basis of ions travel in time of flight. So we'll also discuss that how that could happen. Okay, so that part I believe yesterday Murli sir has been taken part and discussed on that. So this is a single quarter pole. So what we can do, only two way of analysis here. We can scan the mixture of compound and identify the spectra in that sample. Otherwise we can do the single ion monitoring in case if we are focusing for indivisible component in that mixture. So you can ask in between if you have any concern regarding to the presentation, regarding to the point. So we can go in depth into that. Probably I believe that this particular part has been covered in yesterday's sessions. So anything and any point if you wanted to ask, then we can go in depth in that. And so having said that, like we can do two experiments. One is a single ion monitoring, like we can focus any particular component molecule present into the particular mixture. Otherwise we can scan it, that if you wanted to see the profile of a spectra, then you can do the experiment on the scan. And in triple quarter pole, having said that, like we can do the transitions, like we can run and quantify. So most of the time triple quarter pole is used for the quantitation analysis. You can define different component transitions and identify on the basis of their transitions. So confirmation of the compound could happen on the basis of their product masses. So but I believe how it is going to be differentiate from the single quarter pole. Assume that there is a component which having the similar, like if I am talking about 209, then in nature there is a multiple component having the 209 as a molecular weight. And probability, like there is a 209 of the two component having in same mixture, then you are not going to be distinguish these two ions. But what will happen? These two ions would have the different product masses. So basis of the product masses, you can distinguish that what would reach to the detector, because you are filtering on the basis of the product masses, not on the basis of the parent masses. So consider like compound having the same product masses but eluting on the different RT, either on the same RT but would not be considered as the same ion because their product masses would be different. So final filtration in the third quarter pole would happen on the basis of the product masses. So in that way, this triple quarter pole is a more sensitive and for the quantitational analysis. Now on top, so what instrument we are having in FRI, that is the LCMS QTOF. So QTOF is nothing just a HRMS. So we having the high mass resolution instrument. How this is going to be differentiated from the other single quarter pole and triple quarter pole? We are having the top here. So this top gives you the high mass accuracy, high resolution of mass data, and the chronology of the ion movement is that desolvation is happening into the ion source. So source is nothing, just converting the solvent into the aerosol, because we know that the mass is identifying only the ions. So there is a two mode having the different language understanding. One is talking about the liquid phase of chromatography, another is having the ion understanding. So what we have to do, so LC is always working with the liquid phase. Now MS is understanding the ions language, so we have to convert that liquid into the ion. And that's the reason we always recommend, why we are always saying that we have to use the solvent and reagent which is volatile in nature, because ultimately in source we have to separate the ion from the mobile phase, reagent and solvent, whatever we are using in a mobile phase. So after the desolvation, that ion go into the capillary. So we are applying certain voltage so that the different polarity of ion would be attracted towards the capillary. Onwards the capillary, there is an ion guide which actually restricts that ion to diffuse into the vacuum. As we all know that in mass spectrometry, this mass spectrometry is working under the high vacuum. So to avoid that ion which has entered into the mass to diffuse into the vacuum, we are applying a limited voltage so that that ion would be guided towards the quarter pole. And at the quarter pole, as like you discussed, that there is a RF and DC voltages we are applying. That is a limited RF and DC, so that which would be based on the molecular base M by Z. And that particular ion would only travel to the quarter pole and reach to the next level. If we are running the component, like I'm running in a scan mode, then this collision set would work as a scan and all ion would reach to the quarter pole, and there is a pulsar where we are applying the constant kinetic energy, and basis of that kinetic energy, that ion would toss into the top tube, and that top tube. So the time, there is a constant time, like as per the N by Z it would take, and that time actually reflect the back, calculate the back, what exactly the molecular mass of the compound, M by Z of the compound, and on the basis of that time actually we are getting a more accurate mass results. So having said that, this instrument has a capacity to identify the molecule on less than 2 ppm mass error possibility. So what will happen if the error would be high? So consider that there is a molecule having the 165 ppm error. So once we'll go with the data interpretation, so we can also generate the formula on the basis of a spectra. With 165 ppm error, the possibility of formula is 209 molecule. So you understand that, and if there is a 2 ppm error, the possibility of the compound is only 2. So identify your target compound from the 2 is quite easy rather than the 209 is the compound list.
Any idea why this is there? If you increase the mass accuracy, why you are having more confidence? So because in nature, nothing exists as a whole number. There is a fractional mass associated with everything. I think Dr. Vinit covered this, right? There is a fractional mass associated. Carbon is only carbon 12. Rest is 0.008, 0.003. There is a fractional mass associated.
So mass efficient and mass coefficient.
Yes.
Mass coefficient and mass coefficient. Correct. So each mass is characterized by the whole number as well as the fractional masses. Now whole number you can have different combinations. So CH2 and N. CH2 is also 14, N is also 14. But if you look at the fractional masses, there will be a difference. And this TOF can help you to go to those fractional masses. mass of 12, hydrogen has 1.008. So how many hydrogen? If you have 10 hydrogen, you can get that fractional mass from that hydrogen. That is the basis for prediction of formula.
Exactly. So once you are acquired the same data on a QTOF, so somehow you will get the entire isotopic fidelity. So you can identify exactly what exactly the monoisotope of that compound. So assume like we are having a compound and we are having the accuracy at first point of decision. So the formula possibility more than 1000. In that case, if we are coming on to the next level of accuracy, then now the prediction of formula possibility is reduced half time. On the same, if we are going with the third digit, there is a 100 formula possibility, and at the fourth digit, it is less than 10. So the same way we have been explained. So now what we have been increasing, we are reducing the ppm error and getting the less possibility of the compound. And so with this help of this, we can actually target like the concern compound, and we'll get the more meaningful data. So how exactly it is happening? So as having said that, like at a source there is a desolvation is happening, and after the source there is a ion optics which guide the ion to reach to the quarter pole, and after the quarter pole it will go to the collision cell where we are applying the potential difference, and with the help of that we can break that ion into the product masses. Onward the product masses there is a beam shaping. Why beam shaping actually required? Because once the ion is going to be break down, then their trajectory into the same pattern. But what we need like what we want here, all the ions should reach to the pulsar on the same plane, because we are applying the kinetic energy to the ion. So if they will not be in the same place, the kinetic energy would not apply into the same manner. So their time of flight would be differentiated. So to reach into the same plane to the pulsar, we have the beam shaper. With the help of that, all ion which is going to be break down either into the scan passing through the first quarter pole will reach to the pulsar in the same plane. And at the pulsar we are applying the kinetic energy to the all ions so that they will top into the tube and reach to the detector basis of their M by Z. So smaller the ion will reach to the faster on the detector, and it takes very less time. Higher the M by Z value takes the slower their movement into the time of flight and take a time to reach to the detector. So this is a pulsar. On the pulsar we are applying the kinetic energy. So there is a reflector on the top of tube. So any ion which is going to the top on top of the tube will reflect it. So there is a mirror actually which reflects that ion and give the path to the detector. So with the help of that, at the high vacuum we are applying into this top tube. So this is e⁻⁻7 with this version. So we have another models also which is having the similar almost like 10⁸, the maximum vacuum we are applying on the top. So significance of this vacuum is that we are getting a more accurate data. So there would not be any disturbance and distortion on the ionic path of the movement of the ion into the top tube. So whatever the time it is taking to reach to the detector would be more accurate. So the possibility of mass error could be less in that case. So having said that, we are calibrating the mass like top tube on a daily basis, because the reason of calibrating this top tube because these are made of metal, and if there would be any millisecond time difference is going to be happen, that is result the mass error. So to avoid that and mitigate that drift of ion movement and time taken by the ion to reach to the detector, we are calibrating this top tube. So these are the standard time, like 20 microsecond is calibrated for the 118 masses, and 46 seconds for the 622 masses, 90 microsecond for the 2421 M by Z ions. So accordingly, this is going to be calibrated before going to the instrument, any analysis of the instrument, so that whatever mass difference is happening because of the temperature change or extension of the top tube would be mitigated in your sample analysis. So whatever result you would have, that is a more accurate result.
So there is a relationship between the time of arrival of the ion and the mass of the ion. We are re-establishing that relationship every day. So there is an equation called, I will show you in the lab, there is an equation that this much mass, this is the time of arrival. This much mass, this is the time of arrival. So before unknown analysis, we put some known standards and we calculate whether that equation is correct or not. If it is not correct, we establish that equation to suit the current condition of the instrument, and then we run unknown analysis.
And this is the reason actually we are daily calibrating before running a sample on an instrument, so that we can confirm that with the known standard masses, how the response of the instrument is. And this is a system suitability of an instrument, that it should pass less than 2 ppm error. So if there would be any mass defect more than 2 ppm, instrument would result as a fail in calibration.
What is the general standard sample you use to understand the calibration of that instrument?
So these are known synthetic compounds
Which is being given by the
which are provided by us. So you have to, there are 7 compounds, these are all synthetic compounds.
All 7 should be, or either the one of it should
So
be?
it
All
depends.
Depend. What type?
So there is a different mass range you can operate the system. You can operate, if you are working with protein, you will be working in a higher mass range. If you are working with peptide, you will be working at a different mass range. For small molecule, it is a different mass range. So each one depending. So now the 7 masses, as the description shows, 2421, and there is one more mass called 2721, that is our highest mass. So these are the 7 masses from 118 to 2721. If you cover 1700 m by z, you will be covering 5 mass. So it is a 5-point calibration or 7-point calibration.
And one sample should be calibrated before we take up any experiment.
I think before starting any experiment in the day, you establish this relationship.
Calibration of the instrument. If the instrument was idle for a month, then
So first of all, we have to be calibrate the instrument. In case if there is so what happens, there is a two mode of calibration. One is the quadrupole calibration, another is TOF calibration. So if we are doing the TOF calibration, means we assume that on a daily basis, once we are doing the quadrupole calibration, we are actually adjusting the voltages. Having said that, the quadrupole principle is that RF and DC. So we are going to be legitimized that RF and DC, radio frequency and direct current. And we assume that that would only happen once there is some malfunction happen with the instrument.
So this calibration is only for the TOF, meaning it is calculating the time, like from the place the ions enter the TOF tube and reach the detector. The whole instrument as such, if you calibrate, it is called tuning. So that is a different tuning, because there what you do, you make sure that the molecules travel because of the voltages. So you adjust the voltages there. Here you don't adjust the voltages. In calibration you don't adjust the voltages. So if the instrument is idle for a longer time, maybe 1 month or 2 months or 3 months, you will do the tuning of the instrument. Now in tuning, there are different modes of tuning. Supposing some service has happened, somebody has removed some part from the instrument, cleaned it, put it back, then that time you will do extensive tuning. If you have just replaced the capillary and you have just kept the instrument idle for 2 minutes, because it is all in a vacuum, as long as the situation is maintained, it is fine. If you break the vacuum and you pump down the instrument, then you have to do tuning again.
So in case if there is not any electronic parameter is going to be vary, then we have to be only calibrate the TOF tube. So in that calibration, we only adjust if there is any variation in drift of the time, so that we can mitigate that time changes happening for the individual masses. So having said that, like there are different mass ranges, depending on that, on what mass range you wanted to work with the instrument, you have to be calibrate the instrument. So this instrument is for the small molecule, like you are doing the metabolomics and others. Along with that, you can use the same instrument for the proteomics, where the mass size is more than 160 kDa. So in that case, mass range is the same, like from the 118 from the positive side, lower mass, and negative 112. Like in positive there is a 2400, in negative 2700 is the highest mass. In case if you are going with the 10 kDa, like 10,000 mass size, then this mass is going to be extrapolated. So on the time it is taking for the 2700, it is going to be manipulated, like extrapolated with the time, so that it can accurately get the higher masses result also. So once anything is coming to the, so here there is a terminology, like there is a sum of 10,000 transient in one scan. So what transient is that? Any group of ions from the pulsar to the, like it is taking the time from pulsar to detector is one transient. So in one scan it is going to be take 10,000 transients. So you understand that what exactly the speed of the ions, like getting the data points, so that you will get the more quality data. There would not be any miss ions is going to be detected on the instrument, and you will get the more accurate data and precise data also.
Yesterday, Dr. Murli explained there are two modes. One is continuous mode, another one is pulse mode. So this is the first mode. You give a pulse, and that packet of ion travels the top tip, which reaches the detector, that is one pulse. Then you give another pulse, like that 10,000 pulses you calculate together to make a spectrum.
So that pulse is nothing, just a transient. So this we already discussed. So there are different mode of tuning and calibration. So Saurabh has said that, like, there is a one mode is that tuning. In tuning we are going to be calibrate all the voltage parameter along with the top tune. If we are talking about the calibration, in calibration we are doing the quadruple volt calibration as well as the top calibration. In case if your calibration is failing, it means that the ions which is filtering from the quadruple is not accurate. So mitigate that and adjust the voltages. We can do the calibration and time of top calibration, like quadruple calibration and top calibration both. Still, if there is any malfunction and breakdown happen, then we have to be tune the instrument. So it takes time also, because at the time of source till the time of detection, it is going to be optimized all the voltage parameter at time. So after the calibration, like this is actually old software where we were getting this kind of equation value with, like what exactly the time going to be adjusted after the calibration of the instrument. But now we are directly getting the reports where we will get the all equation value in that report itself.
And we will show this in the lab.
We'll do this kind of activity in lab. So there is one more feature. That's the reason this is called dual AGS. We have a two nebulizers. So through the one nebulizer we are like injecting this earth sample, and another nebulizer we can inject the reference masses. So what this actually reference masses does, actually calibrate the time of flight. Suppose we are having long batch sample analysis and there is a probability of temperature variation or anything going to be changed into the lab which can cause the mass shift. So maybe some masses which you are detecting in the morning, maybe in evening that mass is not accurate. So probably your monoisotopic fidelity which you are getting in morning would not be the same in evening. So to mitigate that, we have options to start the analysis with the reference masses. In the reference masses, we have these kind of reference standard masses which you can choose according to your molecular weight. So you have to be like, it is always recommended, choose the reference masses nearer to the value of your molecular weight, so that throughout the analysis this instrument is going to be calibrated. So the chances of the mass shift would be reduced, even I would say rather avoided. So once you are using any reference masses on the TIC spectra, you can see that these masses. So consider like we have been used these two reference masses, one is 121, another is 922. So throughout the analysis, you will get these two masses in your spectra. So it is confirming that the instrument is going to be calibrated throughout your analysis, and you are getting the ions, whatever you are sending as a reference mass into the instrument. So as I said that, like this instrument is working, like there is a two mode. One is a liquid mode where we are going to be convert that liquid into the MS, into the vapors, so that our ion is going to be liberated from the solvent. So we need a source. So according to the molecule's nature, we have a different source. Like we have a ESI, AGS, APCI, and MMI. MMI is nothing, just a multi-mode. In the same source, we have a APCI and ESI mode. So what exactly the ESI does? ESI actually used for the mostly polar molecule. So if we are having non-polar compound, then we have to be use the APCI. APCI nothing, just atmospheric pressure chemical ionization. So in ESI we have a Agilent patented AGS system. So how this AGS actually differ from the normal ESI? We have a extra heated nitrogen gas into that. So what will happen, if you see that if we are using normal ESI, the signal intensity is bit low. Why it is low? Because the desolvation capacity is comparatively with AGS is low into that. If we are using AGS, then we are applying the extra heated temperature of nitrogen into that. So the desolvation is happening faster compared to the normal ESI. So liberation of ion will increase in this source. So intensity almost 1:5 times increase AJS. So whatever the intensity you are getting in normal ASI source, with AJS you will get more than 5 times intensity higher. And in APCI is, I think it's been explained, like we are using the corona needle, so which is continuous bombarding the electron into the solvent. So charge first transfer to the solvent, and after the solvent it will go to like transfer the charge to the molecule. So what this like non-polar molecule which is not going to be ionized in solution, with the help of APCI we can make them ionized. So this is the way like molecule is going to be ionized into the APCI mode. So we having the corona discharge needle which continuously bombarding the electron onto the solvent. So first the solvent, whatever mobile phase and diluent you are using with the molecule is going to be ionized, and after the evaporation the same charge is going to be transferred with the molecule, and molecule would ionize and travel into the body. So the functionality of quarter pole, as is explained in the earlier sessions, like we have 4 parallel rods having the opposite same polarity. So we are applying the direct current as with the radio frequency mode. So we are ramping actually this RF and DC voltages, so that whatever ion we are filtering with the quarter pole, that ion would only pass the quarter pole, this other will drag down with the quarter pole and neutralize. So this would happen. So this would happen like this way. So any ions, like there is a mixture of ions. So once we are applying any RF and DC, then that RF and DC would be maintained for the M by Z value. So you consider it here, all the ions having the limited RF and DC. So whatever RF and DC we are applying, these all ion is limited for that. So that's the reason these all ion would able to pass this quarter pole. If we are going to be change that. So that's the reason, having said that, like there is a 2 mode. One is the scan mode. So in that scan mode, you are giving the range of mass. If you are giving the range of masses, it means that you are giving the high RF by DC value. So that from that range to that, like from initial to 8, whatever range you have defined, that mass range could only pass the quarter pole. If you are going to be specific masses, then you have to be give that particular N by Z. So whenever you are defining the N by Z, this RF and DC would ultimately going to be established on the quarter pole.
So again, this is like you don't have to bother about RF and DC. It is all mass dependent. You have known masses. For that, you know what is the RF and DC. So you will look at only the masses, and that automatically inside the instrument it will calculate what RF and DC is.
So that would be established by the instrument itself. So you have to be only put the mass value.
There is a lot of physics behind it, like what RF, DC and all. But as a user, you don't need to worry about it. You just need to know that this mass will come out at this time using certain settings which the instrument will only do. Only thing you have to calibrate it repeatedly. After maybe 1 or 2 months, you will have to see that, okay, is it doing the job it is supposed to do.
Okay. So, like having said that, we have a limitations and we have a very less number of solvent we can use as a diluent mobile phase for the mass spectrometry. Reason being, if any solvent is like not leaving any residue into the source, that is ultimately going to be deposited into the source, that is going to be clog the capillary, so there would not be any ion transmittance would happen. So ultimately you would not get any response. So these are the solvents which has not been recommended at all with the mass spectrometry, because if we are running the same method on LC, we have a like very large scope of mobile phase selection and diluent selection. But once I am coming to the MS, then we have a very limited, like we have ammonium acetate and ammonium formate as a reagent buffer, formic acid as a acid modifier, ammonia as a base modifier.
If this one of the chemical is present in our analysis, we don't know. When we are unknown chemicals, when we are analyzing, triethylamine may be a chemical present in there. In that case,
So ultimately you are injecting 20 microliter as an injection volume. But assume that you continuously you are injecting the same ion into the source, then that is somehow going to be a problem. As you said that triethylamine, some cases this is used as a buffer modifier to retain some molecule on column side so that you could get a better resolution on the chromatography side. Then there is a demerit, like somehow you are going to be improvise the chromatography, but since ultimately you are getting the 102 not as a continuous, as a high abundance masses. And this is the reason actually we are not recommending this kind of solvent, because this is very sticky in nature.
no, my case is some of the preservative chemicals has this triethylamine
I mean, see, triethylamine as an analyte, you will put in the sample, and that is the reason you are having a LC. So LC, it will bind to a column and it will elute at a particular RT. So you know that this triethylamine is coming that particular RT. You don't have to add your analyte which is of interest is coming at some other retention time. So that is the purpose of LC. It will not allow the mixture to be detected. Only one peak after the other will come. So triethylamine repeatedly will come at a particular RT. You can ignore that peak. If it is a modifier, what Amod is saying is sometimes to make the peak shapes better, to make the chromatography look nice and separate the molecules, people add triethylamine in the mobile phase. And mobile phase keeps on coming continuously. That is the reason we need to avoid triethylamine, because it will interfere with the ionization. Otherwise, triethylamine, whatever is present in the sample will all come. Everything will come in the sample. So if you have, suppose, we discussed plants, right? You saw the presentation from Palampur, IHBT. First they established that pesticides are not there. First they established that pesticide level, because it is difficult to get plant without pesticide. You don't know in the field what all things will be there. Similarly, they established that there is no infection, because if the infection is there from fungus or bacteria, the metabolites from fungus and bacteria will show up. So that is the reason you need to be careful about it. But whatever is there will come.
So in case something,
Some of the experts of HPLC, they are recommending that if you are facing the problem of peeling and fronting in the peak shape, then you should use the key in your
so probably on the chromatography side, there would not be any peak dependent challenge with the mass spectrometry, because we ultimately is not focusing for the peak shape, we are looking for some like ionic abundance. So that's the reason. If you are running, that's the reason. Once you are running HPLC, then you can use whatever modifier is needed to make sure the chromatography looks better.
So this configuration which you have, HPLC coupled with mass spec, you have to consider the mass spec also. You cannot just say I want to do everything with HPLC, then you cannot couple mass spec. So these are the considerations for mass spec. And fronting and tailing, what will you achieve by removing fronting and tailing?
Even there is another.
You should ask that question, right? If you have a fronting or tailing, what will be the problem?
Yeah.
Those are all HPLC reviewers.
I understand. So you understand, like if there is a TIC which is having the tailing, but in the very next moment if you extract the same masses, then peak shape would be better. Why it is? Because the data point whatever required on the mass basis, that is very good. So that they see chromatographic challenges would not be with the mass spec side until, like ma'am was asking, there is a triethylamine in that is sample, then somehow on the basis of sample spectra you can identify, okay, there is a triethylamine. Assume that you are continuously injecting the triethylamine with the mobile phase, then it will continuously come on. Even blind would also have the same masses. Then there would be challenge.
And there are other modifiers. It is not necessary you use triethylamine. If you use acetic acid, it can give the same effect. If you use ammonium acetate, it can give the same effect. So you have to try some other modifier except these.
So in mass spectrometry, like you all know that we can use acid and base modifier. So what our target is that to enhance the ionization. So whatever the range of our molecule pK, then we have to go either 2 unit plus and 2 unit minus, so that we could set and establish the pH of the mobile phase where our molecule would be available into the most abundant ionic form. Then only our ionic intensity would be increased and we'll see that the good intensity of the spectrum. So these are the LCMS grade mobile phase and solvent you can use. Like mostly we are using formic acid and acetic acid for the any positive ionization component. TFA sometimes used, but actually not recommended, but for the increasing the, like I having said that ion pair capacity, then we can use it. For the ammonia which have to be used for the basic moieties, ammonium acetate, ammonium formate, triethylamine and other volatile solvent we can use, which is volatile in nature and not having any residue into the source. So onwards there is a software by which we have to be control the instrument, define the method, and there is some data analytical software also which has been taken by the Saurabh. So I'll invite Saurabh.
Okay. Thank you very much, Amod, for your presentation about instrumentation and LCMS and its technical aspects in detail. So next our speaker is Saurav Naupal sir. So Saurav Naupal sir is working as a Saurav Naupal sir is working as a application engineering center of excellence, Agilent Technology. His area of interest is biological mass spectrometry, biopharma and metabolomics. During his career span of 20 years, he has been involved in life science research at in India Institute of IISc Bangalore and the School of Life Science, JNU Delhi. Prior to join Agilent, he was working as a scientist, proteomics in Paul Life Science, Bangalore. He has authored 12 articles in reputed peer-reviewed journals and has presented several posters at international conferences like SUPO, Congress and ASMS. He is an affiliate member of Human Proteome Organization and has been an invited speaker at several symposiums and workshops. He enjoys creating awareness about mass spectrometry among biologists and training them on workflow. He has published around 10 publications in very good journals and workshops he has conducted and attended, and he gave a lectures around in 16 international symposium and workshops. These all are about brief introduction about this Saurav sir. Sir, if you are ready, you can.
Thank you. So I think the topic is mass spectrometry based only, but we will not go too much into mass spectrometry because I think 2-3 days you will see the instrument, then things will become more clear. So what I want to show you is I want to show you how the data looks actually. So I want to show you how the data actually looks so that you can interpret. And see, you have to look at it in totality. The mass spectrometry, when coupled to LC, why we are coupling it? Otherwise, we can use HPLC alone and mass spec alone. Each instrument has its own advantage and disadvantage. HPLC is a very good tool for complex mixtures. Mass spectrometry is a good tool for pure compounds. That was the thing. But with TOF, now with impure compounds also, I mean, the impure samples, mixture of compounds can also be analyzed. So the HPLC which you have should be high efficient, UPLC, mass spec should also be high resolution for metabolomics. For general single molecule characterization, or if you are looking for one molecule in a mixture, then it is not needed to go for HRMS, or even if you go for a single bond also you can get the data. You know the molecule. But if you don't know the molecule, unknown analysis, HRMS is important. So I'll just show you some of the slides and then so metabolomics is a new technology or new terminology which is coming into picture, but it is not something new to the concept of omics. 20 years people have been working with omics, right? People started working with genomics, then proteomics, then metabolomics now. So the logic of metabolomics is same as other omics, meaning it is not a very targeted analysis. It is unknown, mainly unknown, and as many as possible. So large number of compounds, how to present that data set, how to show. That is the reason all the tools which we use for metabolomics are already used for omics. So some of you have done MSc recently, or maybe when I did MSc 2002, that time we used to learn about all these techniques, and those all omics tools are applied to metabolomics also. Only thing compared to the genomics and proteomics, compared to genomics basically, genomics you have a PCR where you can amplify, but in proteomics and metabolomics you don't have PCR. So that is the reason we use mass spectrometry. Mass spectrometry is high sensitivity readout, highly reproducible, and that is why people use it for metabolomics. Recently it is for metabolomics. Okay, so I would request, please feel free to stop because we are going to spend long time. It is good to have discussion rather than looking at the data alone. So this is the continuum of the metabolomics definition. If you are looking at genes in the group, it is called genomics, and if you are doing transcript, which is RNA, it is transcriptomics. If you are looking at proteins, it is proteomics. If you are looking at the metabolites, it is metabolomics. The challenges associated with metabolomics are different from traditional chemistry. What is the challenges associated? I will establish that. But now, where all you can apply metabolomics? You can apply it to any field which you can think of. Pharma research, plant metabolism, animal, disease research, infectious disease research, everything can be applied with metabolomics. Because metabolites are the end result of metabolism and they affect the phenotype directly. We are all part of metabolomics, correct? We eat something, we metabolize it, we drink something, we metabolize it. All these drugs which we take are looking at our metabolism only. If we are diabetic, we will take some metabolism inducing drugs, right? And especially for plants, metabolomics is a very important tool for plants. And why it is important? Because proteomics generally people do on animals. But metabolomics is very well established for plants because they don't move. Animals, they tend to move and interact, so their metabolites can change. They eat something. Plants don't eat. Right? Plants metabolize only there are only limited inputs into the plant system. You cannot make a plant eat something. It will take nutrition from the soil, it will take air, water, and it will metabolize it. So the metabolism is very clean science for plants. Very difficult to get that kind of samples from animals because they will eat, they will drink, because of the eating and drinking, their metabolism can change. Or even for human, disease metabolism is very difficult. So the challenge with metabolomics is how many number of metabolites? 2,500 primary metabolites, but the number of secondary metabolites can be up to 1 lakh. And that is the challenge. So there is a diverse chemical structure, there is very difficult to establish one single method. One single LC method cannot be used, one single mass spec cannot be used. You have to apply. Variety of techniques have been used. One is targeted metabolomics, another one is untargeted metabolomics. I don't know, you've read about it, targeted versus untargeted, or you are aware about it. If you want, I can talk about it. So, depending on what strategy you want to do, you have to start from the sample prep with that strategy. You cannot start with the sample prep with the targeted strategy and then expect untargeted results. So, what is the objective of this targeted and untargeted? Targeted means supposing I am looking at one particular pathway. So I am looking at, say, glucose metabolism. So glucose metabolism will have a lot of sugars. So my extraction should be targeted at sugars. Or if I am looking at lipids, lipid metabolism, my extraction should aim to extract as many lipids as possible. Then my downstream LC also will be tailor-made for that. My mass spec method will also be tailor-made for that. The objective here is to characterize one particular pathway as much as possible. Supposing there are 20 analytes in a pathway or 20 compounds in a pathway, I want to establish maybe 10 compounds. Untargeted is different. Untargeted means I want to look at all the possible pathways at the same time. Now then I cannot extract lipids, metabolites, sugar, everything together. I need to make some changes. So that is the reason it is important to have this consideration. And this is very important because that is the role where you can play. You should know how well your sample will get extracted, what is the time for extraction, what is the temperature for extraction, what is the stability of your metabolites for the temperature. All these should be aware because this is where most of the inputs from the user will be, sample prep. Mass spec will not change anything if you give a bad sample. If you give a good sample, it will give you the results which you are looking for. And this is very important. A lot of people, they overlook this. DNA and RNA you are not looking at. DNA and proteins. DNA is of course, you can ignore for some time because it is not stable. Proteins should be avoided in metabolites. Otherwise, they will pose a challenge downstream with your analytical instrument. You will end up putting a lot of proteins on the column which will not allow your metabolites to get resolved. So you should be clear, and any good sample prep protocol will have all these steps. Okay, and last step is whether you want to go for LC and BC. These are orthogonal techniques to each other. Why you want to go for LC and BC? Because if you look at the metabolites, they can be nucleotides, sugar, amino acid, lipid, anything. And if you analyze them, you have to use halide, mixed mode, reverse phase, etc. for these polar compound, and for non-polar compound you have to use reverse phase, and this will be mainly with APCI. So in effect, people say one sample, but if you ask me, it is not one sample. It is actually, if you want to analyze the complete characterization, it will be 16 runs. One will be RPLC. If you do the combination now, these many, we have 4 different chromatography, 4 different columns, and then you apply positive and negative. So 4 into 2, 8, and then APCI and ESI. So 8 into 2, 16. Minimum 16 runs you have to do. And then metabolomics, you have to do replicates, minimum triplicates. So 16 into 3, 48 runs. 48 runs for one sample. And then you imagine how many samples you want to do, how many conditions you want to do. So that's much more complex data. Now, I'll skip this in the interest of time because we have discussed it a lot. I don't want to discuss much why you want to do it, why you cannot do it. This is what Amod has already explained, reference mass nebulizer and analytical nebulizer. So this will give you the characterization. Advanced jet stream is also what we have explained. So this is the schematic of advanced jet stream. If you see this ESI, here the plume is very widespread, but because you put this curtain gas, it is limited and it has become less opaque. Less opaque means there is less solvent. Because of this less solvent, the sensitivity increases, and this is the schematic in real time. So if you see, the temperature is changing, and if the temperature is increasing, now the plume which was earlier spread, it is narrowing down. During 5 to 6 minutes, it will narrow down. And this is the inlet for the mass spec. Here the mass spec is inlet, okay? Now what is the effect on metabolites? It is very important. Because of this single advancement, we are able to increase the sensitivity 5 to 6 times. And these are the most common metabolites which we are looking at. Just by implementing this changes in the source, we are able to increase it 5 or 6 times. Okay, I will not go into the quadrupole functionality and the top functionality, we have covered them. So QTOF Mass analyzer, the discussion is over. And this is the part which we were discussing, like it takes 20 micros, and it is very important because what I said earlier, metabolites, number is important. You cannot do metabolomics with 20 analytes. You have to minimum have 2000 analytes. Now when 2000 analytes, any mass spec, any quadrupole based mass spec cannot analyze them. Or if you were to analyze them, you have to run maybe 120-minute chromatography to separate them and give them as a separate peak to the mass analyzer. The HRMS, because of the high scan speed, it can be used for this metabolomics very effectively because you can get basically 1 spectra per second. And if you, the instrument, both quadrupole and TOF is a serial based instrument, like you cannot continuously analyze it, right? So that is the reason TOF is mainly used for metabolomics or any omics for that matter. And this we have discussed, like this is the part which I was highlighting. There is a fractional mass associated with everything, and because of these fractional masses they add up, you can have a distinguishing feature at the 3rd or 4th decimal place. Not at the first decimal place, not at the 2nd decimal place, but at the 3rd place if you see, there will be a difference. And that is where the HRMS comes into the picture. And this is the possible number of formulas, but we will not discuss much about it. Here what I am showing is the efficiency of the detector. So if you see, there are 2 compounds, one is butyl paravel acetate and methyl salicylate, one is a preservative, another one is an antibiotic. If you see, the TOF is able to distinguish them together. It takes, the arrival of these 2 ions will be in microseconds, but still it is able to distinguish them. And not only that, the concentration changes also, it is able to distinguish them. So if you reduce the concentration 150 times, it reduces from here to here. If you change the concentration from 150 times, it reduces from here to here. This is very important for metabolomics because concentrations is what you are looking for. Sometimes it will go down, sometimes it will go up. So TOF is again one very useful for that. Now, next step comes into the picture is how you identify the molecule. What is the step of identification? So you have acquired the data in HRMS, that is bare minimum. You cannot acquire the data in a quadrupole and say I want to identify. You will never be able to identify. First you need HRMS data, but even with the HRMS data, first and foremost is the database matching with accurate mass. That is the first step. If you are able to match, the confidence will be there that you are getting a match. Next step is the match based on the isotopic pattern. Because each element has a characteristic isotopic pattern. You must have read about it, I don't want to discuss much, but when you see the results you will know. Carbon, hydrogen, oxygen, each has a characteristic hydrogen pattern. It is very true for synthetic compounds because halogenated compounds, halogens have a very typical isotopic pattern. So I'll show you some data of that. And then the next step is to do MSMS, fragmentation, and match it based on the MSMS. So the more you match here, the more is the confidence. Otherwise, the ultimate step to match is to get a standard, run it alongside it and establish that this is your compound. Before publication, you have to do that. But if you don't have the standards and metabolomics, you are not getting the identification. Where will the question of getting the standard? Standards are available for some commercially viable compounds, right? But not for secondary metabolites which are present in very less amount in the plant. So for that reason, we apply a lot of bioinformatics tools here. What are those bioinformatics tools? As sir was mentioning yesterday, there is a chemistry and fragmentation. All those things are chemistry based. Now biology based. What is biology based? There are only certain number of metabolite pathways which are possible, right? So if you have a lipid will undergo beta oxidation or some fatness. Certain number of reactions only are possible on a lipid. And the main compound will remain and something will be added or something will be lost at one step or the other. You will miss that modified metabolite because you are not sure of extracting it there. So we have a possibility to match the MSMS based on the fragments only and not consider the molecular ion at all, like you do in DCMS. DCMS has established this very well for that you get the fragments and you identify the molecule based on the fragment. Same approach you are applying now, but not looking at the, so if I get a mass of 230.08, even if I don't match 230.08, so this is the top-down approach, I can go bottom-up also. I can go MSMS match first and then establish the molecular ion. Both are possible. In metabolomics, you have to apply both. So I will not go much into the details. This instrument, you already know what are the advantages of this instrument. It can be used. There are 2-3 things, and this is how the reference mass looks. So if you see, this is the reference mass, this is the peptide data. So you have 322 and 1221. This is the spectra at a particular RT. The moment you change the RT, there are peaks coming in between, but these reference masses are remaining. So you see here, these reference masses, especially for metabolomics because you are running such long batches. You cannot stop the batch and do calibration. So if you are running 40 runs, and also this is important that your runs cannot be very long because if you run the instrument for 3 days, anything can happen, especially in places like FRI. Power can go, power can fluctuate, something can happen. So you have to, we are very mindful. We ourselves don't run instrument unattended for more than maybe 12 hours. And also, that is the reason we have designed this experiment. We will set up the method today and run overnight. And we'll keep the fingers crossed that the run gets over and tomorrow we'll see the data. Because you have replicates, minimum 3-4 samples you have to run. All this cannot be done in a single day. And you cannot do with single runs. Okay? This is what we are looking at for metabolomics, especially. This is a tool, if I mentioned different mass range in the instrument. Now, 3200 M by Z is our mass range for peptide. That is our standard mass range. In small molecules, we have 50 to 1700. Apart from that, we have 50 to 750 and 50 to 250, which is again more targeted towards the mass range which you are looking for. So if you are looking for metabolites, you will be looking for this mass range, which is 50 to 750. So this is a very targeted tuning. Earlier people used to do manual tuning. At least we used to, initial days we used to do manual tuning. But this will, what is tuning in general? Any idea? Any answer on that? How do you tune the instrument? So if you have a musical instrument, tabla, sitar, guitar, whatever, you will tighten the strings, right, before you play, and you will check for the notes. Same thing is here. This is also an instrument. You will put some known masses, you will change the voltages. After changing the voltages, you will see the effect. And then you will establish that these are the best conditions for the instrument, and then you start your unknown analysis. So that you are assured that if there is a detection, it is a detection based on the instrument from the sample. Okay. Then we have another tune called fragile ion tune. Fragile ion tune is a tailor-made tune for metabolomics. So I will not go, we'll demonstrate it in the lab, that will be better. This is how the tuning page looks like. So you have these 7 masses as Amol was mentioning. So you have 322, 622, 922, 1221, 1521, 2421, 2721 is our highest mass. These are the 7 masses, and you can see all of them here. And we will establish the relationship. So we'll do this tuning in the lab, nothing to worry about it. This is how your unknown analysis looks on a mass spec. So if you have a peak which is coming here, this is a brominated compound. We know the typical halogenation pattern is there. We have the second isotope lower and third isotope higher. So we can predict the formula for this based on the carbon, hydrogen, oxygen. So you can see the formula was C6H15 bromine and N. And together with that, you will get the height percentage, and isotopic ratio. It will give you a score based on all this. This is score is 99.73 here, and similar score is observed for this compound, which is 99.73. If you observe closely, it is C6H14. So BRN. So it is only the hydrogen which is changing. Now the instrument cannot tell you whether it is a protonation which has happened during your ionization, or you have ionized the molecule by removal of an electron. That much sensitivity is not there, but remaining others, if you see, none other formula is matching close to this. So you can actually predict the formula right away. And this is how your isotopic pattern will be. If I zoom in. So this red color thing is the isotopic pattern, and the black is our experimental data. So you have to see the ratio of the isotopes which is matching. It should be within this 5 ppm error. And for this purpose only lot of people use the instrument. Synthetic chemistry people use this. This is more closer to your natural product chemistry where you don't have bromine, but C19H15. So this is the ratio of the isotope, second isotope. This kind of analysis is only possible with HRMS, nothing else. And all those things. So now we'll establish something about how you interpret the data. So this is another tool which is called DIA. कुछ कोई DIA use किए हैं? नहीं किए. QTOF and DIA. These are the tools which we use for MS/MS fragmentation. Anyone knows about this? What is data independent acquisition? So we'll explain in the lab also, but I'll give you an overview because in the lab we are going to split it into 2 groups, right? So I'll just explain. So I told you that you have to do MS/MS match, right? So what is the first step for doing MS/MS match? You have to do MS/MS, correct? So how do you do MS/MS? First step of doing MS/MS is to isolate the molecule in quadrupole and then do MS/MS. So one molecule at a time you will get, and you will do MS/MS. But this is okay with your limited analytes. If you have 20, 30, 40 compounds, all okay. Now, the quadrupole, as we know, is not a very efficient filter. You have to give time to the quadrupole. So when you do metabolomics, if 20 compounds are coming at a time, quadrupole cannot pick all 20. It has to pick some of those 20. What are those sum of 20? You will give some establishment, something above this threshold, bare minimum, it should be like this, above this mass you fragment it. It is no use fragmenting a lower mass. If you get a mass of 70, if you fragment, you will get 2 fragments. It doesn't make sense. So if a higher mass is coming, I would prefer to fragment the higher mass. Even after doing that, you will miss 18 compounds. You will not get MS/MS for that. And if you don't get MS/MS, you will not get the library match, you will not get anything. So for that reason, in the instrument, we tell the quadrupole not to fragment one peak at a time, but fragment all the peaks which are coming at a time. So here if you see, it is fragmenting everything from 50 to 150. And this is what we call data independent acquisition. It will take a range of masses and fragment all of them. The problem here, you will not get the molecular ion. But as I explained, molecular ion is not needed. You can go with fragment analyzer and you can do the fragmentation practice. Because you have HRMS. So quadrupole is coupled to HRMS, that is the reason you can do this. Okay, so I will not go much into detail. Now the problem comes with the mass spectrometry part. Your data is good, your interpretation is good, but what is the challenge with mass spectrometry? Hardware is not a challenge at all. That is the established fact that you have lot of places where you will be able to get this analysis done. But compound identification is a challenge. Then biological significance of that compound. Like what is the importance of that compound? Why is that mass coming? Otherwise it is a mass for you. If you get a mass of 273, it does not mean anything unless you establish what is the biological impact of that, right? So this is the part which we will cover about the software. Now for establishing the identity of compound, we have a Metlin library which has 240,000 compounds and 9,452 compounds, which is with spectra, with MSMS. So you choose the MSMS match. Apart from that, there are a lot of bioinformatics tools which you can apply. XCMS, morning they showed, right, there was, what was the tool they used? They used, they used some wine, mass wine, MZ Mine, MZ Mine, XCMS, then Sirius, then you have Mass Bank, you have GNPS. GNPS is Global Network, Natural Product Atlas. All these are tailor-made for natural product atlas. So we are also going in that direction. It is not possible for any one vendor to give you all the. So if the more bioinformatics tool you learn, more interpretations you can do. And our mass spec data can be used for their mass spec. So MS Mind they have shown. I will show you our data, how we can do our licensed software. Now we have launched another tool called ChemVista, where you can directly upload the data to the open source networks and they can establish the identification. So identification, now because of this networking which we do, it is possible. Then the problem with Metlin is that it has compounds from synthetic compound, it has natural product compound, it has so many other compounds. How do you establish that these compounds are from your organism only? So for that we have a tool called pathway to PCBS. If you get a pathway for that particular organism, like you are working with say some plant, I will show you the data. So if you are working with say nicotine, nicotiana, you may not have nicotine data, but you will have the same genus data. So you can make a pathway list, you can establish the library for that alone. You don't have to search all 242,000 compounds. You can search only the compound relevant to your organism. That is possible. Then, apart from that, next we will do statistical analysis. So this is very important. This is the part which we will do tomorrow with our data which we'll acquire. But I'll explain you the basis of this statistical analysis. So whether you use GCMS or LCMS, our workflow is continuously same. So whether you acquire the data on GCMS, DC QTOF or LC QTOF, first step is we will do the feature finding. We will establish the reproducibility of the data. After that we will do the statistical analysis. So now, what is this feature finding? This is how the feature finding is done. So as I mentioned to you, this is the data from nicotine plant, where they have modified certain genes in the nicotine, metabolism of nicotine. So they have incorporated, there is some overlap in the metabolism of nicotine and glycerizer, your moiety. So they have incorporated the genes for moiety into the nicotine. And if you see here, how many compounds we can see? 2,125 compounds. So that many number of compounds and this was in 5 samples, each one having different replicates, and you have to have blank source. So looking at all this data together, it is very difficult unless you have a tool like this. So in this tool, we are able to see the data, we are able to see the compound, we are able to see the abundances here, we are able to see the EIC. You know what is EIC? The concept of EIC, BPC, everyone is clear? What is EIC, what is BPC? Okay. So I'll open this software, we'll see some data so that you know that what we are talking about, what is EIC, what is BPC, okay? So first of all, this is how the data looks. We will see this data in the lab also. This is typical HRMS run. If you select this tool, it will walk the chromatogram. You will walk the chromatogram. You click anywhere, you will know that, okay, what are the peaks which are coming here, okay? So all these are HRMS peaks. Multiple peaks will be coming at each point of time, and you can see this. Now, this is what we call TIC. This is TIC. Can you see here? TIC, total ion current. Now, problem with this TIC is everything is coming and it is represented here. So if you see here, there is a peak of 247, there is a peak of 305, 113. The combined intensity of all this peak will give you this intensity which is here. Okay? Now, if we right click and say extract chromatogram and say extract BPC. So what is the BPC here? BPC means base peak chromatogram. Base peak for any point of time, if I click here, the base peak for this spectra is this most abundant peak, which is 247. So if I calculate the abundance of this peak at this time, which is 247, this is the BPC abundance. So if you see, BPC looks much cleaner than TIC, especially for HRMS. Why? Because in BPC, only the most abundant peak is considered. The background is not considered, or less abundant peaks are not considered. Correct? Now, if I look at this mass of 242.2838, okay? I zoom into this mass, this is the isotopic pattern. I double click on this and I will get the EIC. Right now the EIC is not clear. So what I will do, I will right click and say extract chromatogram, and then I will say EIC and we will establish here 242.283. So now you see we have the TIC, and instead of TIC we have now extracted this peak. So you have this 242 is coming only as a single peak. This is what is called EIC, extracted ion chromatogram. So extracted ion chromatogram for a particular mass is extracted here. It will say which mass. Now you can extract for multiple masses, whichever you want, but this will give you the abundance of this peak. How you calculate the abundance of the peak? Yeah, so either you can calculate the abundance based on the intensity of this peak here, or based on the EIC. Always you will calculate the based on the EIC the abundance, because peak will start from here, right? From here to here it is a peak. So compound is present from here to here. So you have to consider everything. So if you ask me, if I integrate it, and then I say to this that please calculate the instead of chromatogram area. Now this area which you see here, this is what is called the area under the peak, and this area under the peak will give you the abundance. Tomorrow there is a session from Dr. Sanjeev Kanodia, so he will show you. If I have another sample where this area is varying, then I will know that the abundance is varying. Okay? So this is based on the EIC only, the calculation. Now if you see this is not corrected, like there is lot of spike and it is not smooth, I can right click and say smooth chromatogram, and then I can establish the area. So again the area will change because after smoothing something will go down, right? And this is the effect which he was mentioning, fronting and tailing. So this is a peak which is fronting a lot because of the fronting. So ideally the peak should be starting from somewhere here and ending here. It should not be spreading out like this. But this is the trade-off which we give. In mass spec, in HRMS, most of the peaks will be like this because you are not targeting one peak. So you see any other peak here, similarly. So 463.130. So now you have these two EIC. This is 242 and this is 463. But this is coming like a spread into two peaks. The peak is splitting. This is what we call splitting of the peak. Because it is at a higher concentration of organic. So splitting is most likely to occur. If I smoothen this, maybe it will go a little bit okay, but still the peak is splitting. So this, if you apply some organic modifier, this will be avoided. But for the sake of consideration, abundance, we will consider both the peaks. It can be because of the isoforms also. So it can be because of the isoforms, and then in that case, if we consider this is one peak and this is another peak. Okay. Now you can see these are the two peaks. So these are all the data which how we interpret the data, chromatographic data. Okay. Now same thing. You don't have to worry about doing it here. The software does it for you. So if you see this is Profinder, in Profinder, same thing you are getting for each compound. Similarly for some other compound, you are getting the spectra, and from here spectra you are getting the mass, the EIC. So EIC gives me the abundance for these compounds. Okay. Now we have established the data, and we have now got all the peaks together. What we have to do, we have to try to make a biological sense of it. And this is the part which is done in the software tool called Mass Profiler Professional. This Mass Profiler Professional is used for metabolomics, genomics, proteomics, all the top. So if you see here, this is what all you can get. You can get heat map, you can got. Now, problem is metabolomics is all about large number of data, correct? How do you represent the data for publication? This is the tool which will help you. It is a data reduction tool without losing the essence of the data. Okay. So first and foremost, what will you do in this? You can use microarray based data. You can use the gene based data. You can use GCMS based data. You can use NMR data also in this. If you have any Excel based data, you can use it. And what you will do? You will do a pathway centric approach. So I'll show you some example for plant metabolites. Then it will establish that how you will be able to interpret this. And this is the PCA which you will generate. So PCA is principal component analysis. It's a data reduction tool. These are the 5 samples which have been established based on the 3,386 compounds. The abundance of these many compounds were considered to plot this PCA. And with the click of button, you can plot this PCA. Otherwise, you saw the PCA which was present in IHBT today morning. That was a 2-dimensional PCA. This is 3-dimensional PCA. So you have X, Y, and Z axis. Each axis represents a component of these entities. So X axis, supposing Y axis means if something is separating on y-axis, that means it is based on 22% of these compounds. So there are books written on PCA, but it's a very useful tool to establish, and these are the replicates. So you can see the two replicates which are over there. Okay? So now let us see how this data will be interpreted for some plant sample. So this is the old presentation, that's why the format has changed. So now you see the profiler data for most of the peaks which we are showing here. Okay? And then what we do the filtration of these peaks based on the fold change. Because you cannot do absolute quantification. Absolute quantification you need to have standard. But if you have two samples, one sample which is having abundance, another sample is in another abundance, you can do a relative quantification. And relative quantification with fold change, right? I don't know what amount, but it should be more than 2 or 3 times, whatever you want. So that is the filtering we do. So this is the data for one of the components. Now, if you see there are various so this is how you can establish each line here is one data set. Okay? Each compound is a line in one so here if you see in this control, this is the abundance of these many compounds, that is the abundance, and how they are varying across different samples. That is what it is showing. This is one way of representing data, multiple data sets. So these are 3000 compounds which are represented here. That's how it is changing. Now you can pull out the things which are needed for only the and when 5-way Venn is another way of establishing it, right? So you can do this Venn diagram based on the fold change. First I will get the data, then I will apply fold change. After applying fold change, I will get that how many peaks are abundant. So if you look at these 233 components which are present, they are, no matter what you use, you are coming to those compounds. These are all tools to establish. Then next step is pathway analysis. What we will do, we will take the established pathway and we will look for these differentially expressed compounds in those pathways and we will match it. So if you see here, the ABC transporter, the number of pathways which you are getting, the number of compounds are 122, but I am matching 5 compounds. What are those 5 compounds and where they are matching in the pathway? This is what we are looking at. So you are getting the abundances of these compounds, you are getting the abundances here. So it is a relative abundance which is here for this compound. In one sample it is low abundant, in both the duplicates, in another sample it is expressed higher. Similarly for some other compounds in this pathway. So all this is possible. Same thing you can see here for some other compounds which were identified using reverse phase APCI experiment. Now this reverse phase is a chromatography, APCI is the source which we have used. This will be establishing for mostly polar, non-polar compounds. So if you see here, these are the different sets of pathways which we are matching. These pathways which are established with one match is not a very good hit, so I would not consider them. But things which are matching with more than 5 pathways here, the topane, piperidine, pyridine, alkaloid biosynthesis pathway. So these are mainly alkaloids which have come in this. Similarly for other compounds and where they are matching in the pathway you can see here. So this becomes very interesting. I mean, if you want to do, then we come to the same sample and how it was analyzed using ESI helix samples. So ESI is, as mentioned earlier by Dr. Murli, it is mainly for the Polar or non-polar? Polar compounds. And helic. Helic is what the chromatography. So what is the helic chromatography used for? What is the full form of helic? Hydrophobic interaction, liquid chromatography. What is the purpose of using helic?
Reverse phase chromatography. It's like polar and non-polar both interaction would happen on the chromatography. So this is hydrophilic lipophilic interaction. So any mixture which is having the hydrophilic like polar and lipophilic like non-polar component, so interaction would be better in this process.
How does reverse phase work? What is the mode of interaction in reverse phase? Correct. Both are so. So helic chromatography, you bind using, what is the gradient for helic chromatography? So column is something which is provided, the gradient is what you have to establish. Helic chromatography, you will bind with organic and you will elute with water. So you will elute with the gradient of water. Generally the helic chromatography was not so popular earlier because the peak shapes are not great in helic chromatography. But using this metabolomics, it is giving the orthogonal separation. Things which you are not binding on RP, you will bind on helic. Once they are bound, you will elute them in helic. So you bind with acetonitrile, 90% acetonitrile, and you elute with water. So how does it work? With acetonitrile being abundant, hydrophobic patches are exposed and then they are interacting. With water coming, the hydrophobic patches go inside and they lose interaction. So they come, the compounds come out. So it's not a very well established, but we don't worry about the peak shapes. So that is the reason helic has become more popular because of this metabolomics. And if you see in metabolomics what we do now, so if you see here, these are the various helic based data. So you have this is the PCF for the compound, which is the control, and you can see the duplicates of the each sample which are here. Similarly, we have done this for another helic ESI experiment where we have considered and how you will match it to the pathway now. So if you can see here, this proline, hydroxy carboxylate, D-proline, L-proline, both are being matched here, okay? And then some other compounds. Now all these boxes which you see here, these boxes are the enzymes. If you do proteomics and you are getting the hits for these again, that these are differentially expressed, then your publication will become much more impactful. That the enzymes are also from the same pathway, the metabolites are also from the same pathway, both are getting upregulated or downregulated. So similarly, for some other pathways, we have done this data. I mean, I don't want to go into the detail. After that, what you can do now is you can look at the pathways alone. What we are doing is a Venn here. The Venn is for the pathways. How many pathways are upregulated or downregulated based on the experiments which are different. So there are different components, and you see, no matter what you consider, these 16 pathways are differentially. No matter what computation combination you use. Okay? Same thing, you can do this pathway count based on the experiments which you are looking for. So this is based on the reverse phase, helic. This is based on the APCI, helic ESI, RP ESI, and ESI reverse phase. So no matter what you do, there are 9 pathways which are implicated. So pathway has components which are hydrophilic, pathway has components which are hydrophobic. If you establish this kind of orthogonality, the impact becomes more, right? So same thing with different pathways which we are establishing, and then this is the conclusion for this. So Nicotiana, the pathways are not available. We use the pathways for solanum tuberosum, which is our related compound. And you can do this, 53 pathways were more or less coming as a upregulated or downregulated, no matter what you use. And the PCA and all those things which we have established. Sometimes with PCA also you can see the data very clearly, because it is very easy to get lost with this kind of data. You know, so many compounds, so many pathways. So MPP helps you to establish those. I have the software here. I can, any questions, because then we can establish MPP. If you want, I can discuss qualitative. We have discussed qualitative analysis is here. Quant, you have any data? Quant. So quantitative data we can show, but that part is going to be covered by Dr. Sanjeev Kanodia tomorrow. Quantitative data analysis and qualitative. We can also do. He may explain theoretical. So we'll explain practical. We'll show in the lab. Any questions here? These are the concepts behind which our whole experiments work. So then when we go to the lab, you should know that what we are looking for.
Sir, thank you very much for your detailed presentation on metabolomics workflow and data interpretation of small molecules and its representation by using different tools. And if you